explaining question 11 from exam 1. So in this problem, we're given the electric flux density vector D in 4 regions along the z-axis. We're asked to find the surface charge densities that are producing this electric flux density field. And those surface charge densities are at the plane z equals 3, z equals 0, and z equals -3. And that's because whenever there is a change in the normal component of D, that change corresponds to free surface charge density. So you can make a diagram to help visualize this problem better. You can start by drawing the z-axis and marking the planes at z equals 3, z equals 0, and z equals -3. These are the boundaries where D changes. At each boundary, you can imagine a very thin Gaussian surface crossing the plane, and the top face is just above the plane, and the bottom face is just below, and both faces have the same area of S. So this is S on the top, and this is S on the bottom. And the sides don't actually matter because D is only in the z direction. And then you can label the values of D. So this blue marker here, this blue vector represents your electric flux density vector for z is greater than 3, and that's -1 a sub z, so it's going downward in the z direction. And then between 0 and 3, you have -2 a sub z, so that's going from the bottom of this, the bottom of the first Gaussian surface into the top of the second. And for -3 to 0, we have a positive electric flux density vector, so that's going from the top of this last surface into the bottom of the second one. And for z is less than -3, we also have a positive value, so that's going into the bottom of this final surface here. So the key equation, or the key formula we will be using for this problem is Gauss's law in terms of D, which says that the total flux of D leaving a closed surface is equal to the enclosed free charge. So applying this to the Gaussian surfaces across the plane, you could say that the contribution on the top face is D just above the plane times S. So this is equal to S here, and on the bottom face, the contribution is D just below the plane times -S. And that's because the outward normal on this bottom plane points downward, and it's pointing upward for this top. So that's why this is positive S. And together these equal the free surface charge density times that same area. So you have rho of S times that area S is equal to the contribution just above the plane times that surface S plus the contribution just below the plane times -S. So if you cancel out the S's here, you can get that the surface charge density rho of S is equal to the contribution just above the plane minus the contribution just below. So now we can go ahead and apply these to our individual cases. So at d equals 3, I have rho of S is equal to the contribution just above, which is -1, right? Just above, we have a -1 value for our electric flux density vector. So we have -1, and that's minus the contribution just below, which is -2. So that's minus -2. So we get that at z equals 3, the surface charge density is +1 coulomb per meter squared. So that's one of our answers. So now at z equals 0, we can go ahead and do the same process. So just above, we have the -2, and just below, we have a +2, so that's minus +2, and that's a -4 coulombs per meter squared. So that's our second answer. And finally, we have a -3. We have a contribution of +2 going just above, and +1 just below. So that's 2 minus +1, so that's also +1 Coulomb per meter squared. So there you have it. At z equals 3, the surface charge density is +1 Coulomb per meter squared. At z equals 0, it's -4. At z equals -3, it's +1. And the main takeaway from this problem is not really these answers. It's more of this this rule here. In that the surface charge density always equals the change in the normal component of D across a boundary. So whenever D changes, that change represents free surface charge. So now that we've seen where this formula comes from, let's look into how this boundary condition shows up in other situations. So I'm going to go through a few examples to show that it's not just for the horizontal planes in the exam problem, it's a general tool for any kind of surface. So let's first take a conductor. So we have a infinite conducting surface below z equals 0, and inside the conductor D equals 0, because in a ideal conductor there's no electric flux density. So and then right outside, D points normal to the surface, and I've labeled that D outside. So applying the formula, we get that the surface charge density, rho of S, equals the contribution outside minus the contribution inside, and there's no contribution inside, so we're just left with surface charge density equals the contribution outside. And for the second example, we'll go over an infinite sheet of charge. So by symmetry, the field is has the same magnitude above and below, but points in opposite directions. So above, dN equals plus D, below dN equals minus D, so we get that the surface charge density, rho of S, is equal to plus D minus negative D, so that's 2D, and we get this very standard equation for a sheet where we have the surface charge, or we have the electric flux density equal to 1/2 of the surface charge density. And finally, we have a vertical boundary at x equals 2. On the left side, D equals plus 2a of x. On the right side, D equals -4a of x. So the normal direction here is along a of x. So the formula is that the surface charge density, rho of S, equals the contribution from the right minus the contribution to the left. So that's -4 minus 2. So we get a contribution of -6 coulombs per meter squared for the surface charge density. So notice that nothing about the formula changed. Before we said above and below for horizontal planes. Here we say left and right for vertical planes. So as long as you stick with the normal direction, the rule applies to any surface orientation. So the key idea that ties all this together is that for conductors, the surface charge equals the field just outside. For sheets of charge, the discontinuity across the sheet equals the surface charge. For vertical or tilted planes, you just use the left and right instead of above and below. And the deeper takeaway is that the surface charges are exactly what create discontinuities in the normal component of D. So whenever the flux density jumps across a boundary, that jump is the free surface charge density. And that's why boundary condition isn't just a one-off exam formula. It's a fundamental rule you'll use in a bunch of electromagnetic problems.